Hello. So did you try this question? The answer is this. So the critical values are 324.02 up to 325.98. And you have to standardize these two numbers using 324 as the mean. So subtract this and divide by standard error. Z is the standard normal distribution, and then you obtain these numbers. And then the type 2 error probability, if you use a standard normal distribution calculator, you can find the probability is this. So the answer is E. Answer is E. Type 2 error probability is 48%. As a comparison, I'm going to consider 320 instead of 324. So there is a bigger difference. Now it's easier to detect. So find, given this number, now again find the type 2 error probability when the truth is 320. Pause the video and try it by yourself. I'll show you the answer. The answer is 0%. Because now everything is the same, but the standardization uses 320. 320 is the mean now, because that's what you assumed. And then the standardized numbers become 8 and 11, which is a huge number. Do you remember? The standard normal distribution, most of the probability lies between plus minus 4. But this probability is away from away from the center, so there is really small probability between 8 and say 12. So it is 0.0000000%. You can find it how small it is on a calculator. So you see now in this case, type 2 error almost never happens. Then what causes the difference? That's because the null hypothesis is 325, but say that the correct aspirin should have 325 milligram. But there are two fake drugs. One has 324 milligram and the other has 320. So 1 milligram difference and 5 milligram difference. Bigger difference will be easier to detect, right? So easier to detect, so almost always you can reject this fake drug, right? However, if the difference is only 1 milligram, then it's too similar to the correct amount. So almost 48% you can't distinguish the fake from the original, the fake from the correct drug. So that causes this much difference. So very surprising result. Okay, another thing I would like to introduce here is the power of a test. The power of a test is actually the flip side of type 2 error. So this is defined as the probability of rejecting the null hypothesis when it is wrong. So the null hypothesis is wrong, then you should reject it. If you do correctly reject the null hypothesis, then that is the power of the test. It is the power to detect a wrong hypothesis. Then think about the relationship. If you assume that the null hypothesis is wrong, if you reject the null, then you get power. If you cannot reject, then that is type 2 error. So power plus type 2 error probability is always 100%. So in this case, power is about 52%, and here the power is about 100%. So calculating the power is pretty much the same as calculating the type 2 error probability, but at the end, change the probability to the complement. So 100% minus type 2 error probability is the power. Okay, then as another example, I'm going to consider waning immunity issue for COVID vaccines. I got a booster shot already. So also again, this is not based on any medical facts. So I made up this example after reading a news article. So don't believe its content, like medical content, but just use it as a statistical example, right? Suppose that someone, let's say I believe that the immunity decreases to 50% level 6 months after getting a COVID vaccine. So its efficacy drops drastically 6 months after getting the shot. Let's test it. So first, we are going to set up the basic structure. We will randomly choose a person who had a vaccine 6 months ago, right? That's the sample. And we define a random variable in this way. X equals to 1 if this person, randomly chosen person, has antibodies, right? And otherwise 0. So has immunity, does not have immunity. And we are interested in the probability of people who have immunity at 6 months after the vaccine, right? And remember, this is the binary distribution structure, and we will study how to calculate the type 1 error probability, type 2 error probability in the binary structure. And we are going to define the hypothesis in this way. So we believe that the probability of having immunity is 50%. The null hypothesis is probability equals to 0.5. And due to the binary structure, this null hypothesis implies standard deviation. The standard deviation can be calculated as the square root of p times 1 minus p, probability of success times probability of failure, which is simply 0.5 times 0.5, so its square root is 0.5. So your null hypothesis implies a specific value of the standard deviation. And now you sampled 100 people and found only 42 of them had immunity. In this case, first step is to calculate the critical values. Use 10% significance level, and then what are the critical values? Pause the video, try to solve it by yourself. The answer is B. B is the answer, because critical values are calculated this way. Mu 0 is 0.5 in the null hypothesis, and z value is 1.64, which is implied by 10% significance level. And standard deviation, S, is calculated as 0.5, and sample size was 100. So, like, if you calculate this number, you will get 41.8% up to 58.2%. So you believe it is 50%, but you allow plus minus 8.2% point. Then, can you reject the null hypothesis? Like, use this data. We have data here. The answer is no, because from the data, the sample average is 42%. Sample implies 42%, which is in between, greater than the lower critical value. It's between those two, right? Therefore, you cannot reject the null hypothesis. So you allow plus minus 8.2%, but here 42% is within that margin. So you cannot reject. The answer is no. Now let's go the other way. We had the result. Now you have to worry about if the result is an error or not. So you did not reject the null hypothesis. If it was an error, then what error is it? If it was an error, what error can it be? Think about this. The answer is type 2 error, because I said type 1 error happens when you reject, and type 2 error happens when you do not reject. So in this case, you did not reject the null hypothesis. Therefore, if it was an error, it should be a type 2 error. It cannot be a type 1 error. So now then, let's calculate the type 2 error probability under the assumption that the truth is 0.42. So probability was actually 42%. That means the data had no random error, was correct, very correct. But what is the probability that you fail to detect your wrong belief? So that is calculated this way. Type 2 error happens when you do not reject. You do not reject when x bar is between two critical values, like this, right? And this will be standardized. This probability will be standardized using this assumption. But so far, it's exactly same as what we did in the earlier example, but there is one major difference. An important difference is that you need to use this assumption to calculate the standard deviation. So when you believe that the true parameter is 42%, it affects, of course, that is the mean, but at the same time, that changes, that will determine your standard deviation because of the binary distribution structure. In the binary distribution, standard deviation follows directly from the parameter p, single parameter p, so you have to consider that. And in this case, it's not a clear number, and I will simply approximate it to 0.49. So you have to use the assumption in here, 42%, and standard deviation here. So this is the major difference of binary distribution from the earlier examples. So when you use binary distribution, remember what you are assuming, what is the true value to what is the truth, and based on the truth, you have to adjust your parameters for the sampling distribution. That's what I wanted to show you here, and as a result, the probability is 51%. More than half, you will fail to detect a wrong hypothesis in this case. That's what it says. Okay, this is it. Today we learned how to calculate error probabilities. So there are type 1 error, type 2 error, and then we learned how to calculate them, right? In the next video, we will start the second part of this chapter, which is quite different from this topic. So we will start a new topic in the next lecture. Okay, thank you for watching, and see you later.